All right, in this lesson, we're going to talk about series. In the previous lesson, we just talked about sequences. So a sequence looks like this, and we could talk about what the sequence is doing as n goes to infinity. We did that in the last lesson. A series is when we add the terms of a sequence, and here we have two series that look pretty similar, but they have a really big difference in what they add up to. So we know that this is approaching 0. Each term is getting smaller and smaller. This is geometric, and we know from before that we can just take the first term and have 1 over 1 minus the common ratio, which is 1/2, and that it adds up to 2. So if we add all these up and we never stop adding them, they will equal 2. This goes to infinity. So we have just a slight difference in how they're progressing, and it turns out this one, when we add them all up, equals infinity, but something that looks pretty similar to it only adds up to 2. And that's called the harmonic series. So let's analyze this series. Graphic, numeric, and analytic. So this is what we talked about in the previous lesson, just writing out the sequence. But now we can have the sequence of partial sums, which would just be the sum of the first number. Then we'll have the sum of the first 2. If we add the first 3, and here we have, if we add all of these, there's the fourth partial sum, and we're trying to find out what's happening to these numbers. What are they approaching? So if we look at a graph, we can graph the sequence at 1, 1, and let's put the sequence as a square. At 2, we go to a half. 3, we go to a fourth. And we can see that the sequence is going to 0. Let's plot the partial sums, and that will be at, with a point, we'll go to 1.5. And here we'll go to 1 3/4, and then closer and closer to 2. So we can see that these partial sums are approaching 2. And we saw that the sum of infinite terms of a geometric series is A1, 1 over 1 minus r. And here we have the first term of the sequence. So we already saw how that equals 2. And we see that Sn converges to 2. Okay, pause the video and try that one the same way. And here we have to start with n equals 0. So I put a 0 there. 2 over 3 to the 0 is 2. Then we'll put a 1 in place of n, and that'll be 2 over 3. Put a 2 there, we get a 9. 2 over 9. 2 over 27. And 2 over 81. Those are the terms of the sequence. Now we have to add them. This says add all of these terms, add all of the terms, and never stop adding them. So let's see what's happening to the partial sums, the sum of the first term. Then we're going to add these. Add the first two terms. We'll add all three of these terms. And we can see clearly what's happening here with these. This sequence of partial sums is approaching 3. We could see that on a graph. So let's just plot the partial sums. At 0, we go to 2. At 0, 2. At 1 is 2 2/3. 1, we go to 2 2/3. Here we go to 2 8/9. So really quickly, it's going up close to 3. And if we see that it's geometric, the common ratio, here we're multiplying by 1/3 times 1/3 every time, so that's the common ratio. And we have sigma n 0 to infinity. If we write it like this, then we can really see that there's the common ratio. The 2 is not raised to a power, so it can just be in front. So we know that the common ratio equals 3. If the common ratio is less than 1, then we can use this formula. The first term, 1 over 1 minus r. Three over 3 minus 1 over 3 is 2 over 3, and then we will multiply by the reciprocal, so we get 3. All right. Pause the video and try this one. So when we're looking at the partial sums, we might think, okay, it's getting close to 2, and then it goes over 2. And then we might think it's going to get close to 3, and then it's going to go over 3. Here it didn't go over 3 yet. And if we just put in 100 and we add up all of those, it's just going to keep on getting bigger. Whenever we think it's going to stop or approach a number, then it just goes beyond that. So when we look at the graph of the sequence of partial sums. At 1, we go to 1. At 2, it's 1.5. And we go to 1 5/6, 2 1/12, 2 17/60. So it just keeps on going up. It doesn't curve down and flatten out. It is curving down, but it never flattens out. It doesn't converge. So we know that the limit of Sn, as n goes to infinity, equals infinity. We can't tell this by looking at the table and the graph. If we continue to check values of n, we'd be more confident that that's true, but we haven't proven this yet. And as of now, we're just going to accept that. Okay, so now we just want to start to deal with the difference between a sequence and a series. Because sometimes you can make a mistake when you're thinking about what the sequence is doing, but you're supposed to be thinking about what the series is doing. All right, so here we have these are terms of a sequence, and the question is asking, what's happening when we add all of these together? Here we have again terms of a sequence. What's going to happen when we add them in the series? All right. So the question is, here we see that the sequence goes to 1, but what does the sum approach? And here, all right, so for each of these, write down what the sequence is approaching, and then write down what the sum is approaching. Pause the video and try that. So in this one, the sequence values are going to 1, but if we add all these up, eventually it's going to just be like adding 1 plus 1 plus 1 plus 1 infinitely, and that means this is going to diverge. The sum diverges. Here, the sequence is going to 0, and the sum, turns out we can't tell what it does, because if you think back to this problem, here we had a sequence that was going to 0, but the sum diverged. So we have to be careful that just because that's converging doesn't mean that the series will converge. Okay, and over here we have the sequence is going to 1, is converging to 1. The sum is, again, we're just going to add up 1s infinitely, so the series diverges. And here we have the sequence diverges, and the series must diverge. So based on these graphs, as of now, we only have a test. We are only sure that a series will diverge. We don't know if a series will converge based on looking at the sequence. So this leads us to the nth term test for divergence. And that's what we saw in the graphs. If the limit is not 0, then the series diverges. And I wrote a sigma notation, adding up the terms of a sequence. You could also write the sum, the sequence of partial sums. And we saw that here. The sequence does not go to 0, and the series must diverge. The sequence does not go to 0, the series diverges. The sequence does not go to 0, the series diverges. We also have this. If the series converges, then the sequence must go to 0. So we will use this more often than that. All right, so we have that one test we can use, and now we see, all we have to do is look at the sequence. What's happening to the sequence? What's the limit of 2 to the n as n goes to infinity? Well, as this number gets large, and the limit is infinity. If the limit is not 0, then the series diverges. And then we can say why it diverges. We just say it diverges by the nth term test. All right. So let's look at what's happening here. The limit as n goes to infinity. And we could see what's happening here if we made a table and we had choose a large number here and a large number there, factorial, like 100 factorial. Here we have 100 factorial times 2 plus 1. Well, that 1 is going to make less and less of a difference when we start comparing these really big numbers. So it turns out this limit is a half, but it's still not 0. So then we would say that the series diverges by the nth term test. Let's see what's happening here. The limit as n goes to infinity of 1 over n equals 0. And we don't know what happens. The nth term test only says that if the limit is not 0, then the series diverges. Here, the limit is 0, and it's inconclusive. The nth term test does not apply. And this is the harmonic series. And I said earlier that it diverges, but the nth term test will not work. And pause the video, do the same thing on these. So we want to look for the limit as n goes to infinity of 1 over n squared. So as the denominator increases, the fraction decreases and it approaches 0. If the limit is 0, then the test does not apply. We're just looking for when the limit is not 0, and then we know that the series will diverge. We'll see later that the series does converge, but we need a different test. So let's check that one. The limit as n goes to infinity, 3 over n. As the denominator increases, the fraction decreases, approaches 0. So again, nth term test does not apply. And we've seen in pre-calculus that it's possible just to cancel these and we'll get a 1 over 3. We look at compare the highest exponents. In calculus, we have something called L'Hopital's rule, where we can, if we get infinity over infinity, which is indeterminate, then we can just use the limit and do the derivative of the top, 2n plus 1, derivative of the bottom, derivative of the numerator, derivative of the denominator. We still get infinity over infinity, so we can do the derivative again. This is called L'Hopital's rule, and we get 2 over 6, so that's 1/3. The limit is not 0. So we know that the series diverges by the nth term test because the limit of the sequence is not 0. So we really want to emphasize that we know the difference between the sequence and the series. If you see this in front, then that's the series because we're adding. Here, if we just wrote them out, we just have commas to separate them. And that's the end of that lesson.